All right, so I thought I'd have a go at giving you guys a few example problems about pulleys that are usually on the IB exam, although you're not going to have to do the IB exam, but these are pretty common problems because it's very interesting to see the acceleration of a mass on a pulley not doing what we'd actually predict. So when we were focusing on the mechanics suit in chapter 1, if I would hang a mass on a pulley and I'd say that the pulley is frictionless, everyone would assume that the mass would fall with the acceleration of gravity. So the acceleration of that hanging mass will be 9.81 meters per second squared. But if we attach the pulley together and we actually did some video analysis and measured the acceleration of the hanging mass, we would all find that that acceleration is less than 9.81 meters per second squared. And in your lab reports in grade 11, you would have said, well, that's because of friction inside of the pulley. It doesn't rotate that fast. Well, in all reality, we never told you that we have to factor in that the mass of this system has inertia. So the pulley has inertia, and a force has to be applied to get it rotating. All right, so the acceleration is going to be less than the 9.81 because the object is not in free fall. The force of gravity is working against the inertia of the pulley itself, and some of that force is going to have to be used up to get that to rotate. So a very common engineering problem, beginner's engineering problem, is to try to figure out in this complex situation, what will that linear acceleration of that hanging mass be? And I want to just help you figure out how to set up these types of problems, okay? So first of all, let's just do a quick review before we come back up here and take a look, all right? So a few formulas that we had before is that the sum of the torque of a system is going to be equal to the inertial mass of the system times angular acceleration. All right, and that was the equivalent of, for example, F equals ma for a linear system, okay? So the force applied to a point mass is going to make it linearly accelerate. That's what we have on this side. And then the sum of the torque, force at a tangent, and the inertia of a system, the torque is going to be directly proportional to the angular acceleration. And finally, the angular acceleration times r, the radius of that pulley, is going to be equal to my linear acceleration. These three formulas are incredibly important when we're trying to figure out things such as the acceleration of that hanging mass in the pulley. Okay, so how do we set this problem up? Okay, well, first of all, we can say that I'm going to just redraw a pulley over here. So if I had a pulley, okay, and a hanging mass, okay, the force of gravity on that mass, what's counteracting that is the force of tension. So if I'm trying to calculate the linear acceleration of that pulley, the force of gravity minus the force of tension in that string is going to be equal to mass of the system times linear acceleration. Okay, that's an important relationship that we developed, relationship number 1. Okay, so Fg minus Ft is equal to mass times acceleration. Okay, the linear acceleration. And then relationship number 2 that we're going to be working with, and I'll rewrite later on, is that the sum of the torque on the system is going to be equal to the inertial mass times angular acceleration. So what's causing torque? What's causing torque in this system over here? Well, torque is going to be the force of tension in that rope. Not the weight of gravity, but the force of tension in that rope is going to be the actual torque. And then r is the radius of that disc. So torque is going to be equal to the force of tension times r is going to be equal to the sum of the torque in that example of a pulley on a wall. Okay, so what I'm going to do right now is I'm just going to transpose all this down below. Okay, just to rewrite these relationships, just so we can get things organized. Okay, so we had that the torque, the sum of the torque, is equal to the force of tension times r. That was an important relationship. Okay, then the other relationship we had was that the weight of that countermass minus the force of tension in the rope is equal to mass times acceleration. And the third relationship that we need to do is say that linear acceleration is equal to my angular acceleration times r, the radius of that pulley. Now with all three of these equations, we'll be able to derive an equation for linear acceleration. That's what we're after. What's going to be the linear acceleration of that hanging mass? down the system, okay? So with all that together, we can figure this out, okay? So I'm going to start off by putting things together. So inertial mass times my angular acceleration is going to be equal to the sum of my torque, which in this case is just the force of tension in the rope times r, okay? So if I put that together, my inertial mass times angular acceleration is equal to Ft times r, okay? Now, using equation number 2, I can substitute for Ft, all right? So my inertial mass times my angular acceleration is equal to ma, the linear acceleration, minus mg minus ma, my linear acceleration. Okay, that's going to be equal to my force of tension times r. Okay, and then I can do a variety of things to solve for my linear acceleration from here. All right, so I can look at, for example, I can substitute angular acceleration. If I'm trying to solve for angular acceleration, I can do some things. Or if I'm just trying to solve for linear acceleration directly, I can go and substitute this angular acceleration for something that we already know. Angular acceleration is equal to linear acceleration divided by r. So why don't we try to do that? My inertial mass of the system is equal to my linear acceleration divided by r, which is equal to mg minus ma times r, okay? And so now we just have to play a game of trying to isolate for a, okay? So how are we going to do that? So first I'm just going to distribute this r into this relationship here. So I'm going to have I times a over r is equal to mgr minus ma-r, sorry, okay, and then I'm just going to try to isolate the a on one side, so I times a over r plus ma-r is equal to mgr. Okay, now I can pull my linear acceleration out of this system here. Okay, so then my linear acceleration is going to be a times I over r plus mr, sorry, is equal to mgr. And then my linear acceleration is going to be mgr over I over r plus mr. Okay? All right, and I bet you could even simplify that relationship even more if you wanted to. But we have all the variables to find out my linear acceleration. Now I would have the mass of that counterweight. I would then have g, which is the acceleration of gravity. I would then have r, the radius of the disk. The inertial mass of the disk, okay, what I would have to do for the inertial mass of the disk is I would then have to go back and plug in this equation. So remember that every object, every shaped object, this is a solid disk. So that's the equation for the inertial mass of a solid disk. If it was a hollow disk or vice versa, there's different equations. I gave you guys a picture containing all those inertial mass formulas. So you'd plug that formula, okay, in for the inertial mass. I'm not going to do that here. Okay, and that probably gets rid of the r over here. Okay, and then creates a total formula where as long as I know the mass of the disk and the radius of the disk and the mass of the countermass, I'll be able to calculate the linear acceleration.